So I think it's 3:30. Okay. Thank you all for coming. I was a little curious to see who might show up here for what is obviously an unusual talk for such a conference. I'm afraid that nothing I tell you here will make you a better programmer. On the upside, there's nothing here you need to remember, so you can kind of relax. But I think it's useful to have some kind of idea of the background behind today's computer technology. The computer was not invented by Steve Wozniak. It goes back a few more years than that. I have, wow, I should plug this in, huh? Yeah, so it doesn't go out. Sorry about that. And I thought I was all ready, and that's the wrong one. And there is an outlet right there. That's good. Okay. Sorry about that. I have an interest in what's called the prehistory of computing. Anything prior to 1940 is considered the prehistory of computing because it was really in the 1940s that people figured out the general concepts of what a digital computer is supposed to do. For anyone interested in the prehistory of computing, one of the places to visit is the Science Museum in the South Kensington area of London. They have some of Charles Babbage's machines on display there, as well as a few oddballs, and this is one of them. This gorgeous assembly of brass and wood is what a computer looked like in 1872. This machine is about as tall as a person. It's on display on the third floor of the Science Museum in London. There is no rush to see it. The machine has been in the possession of the museum for 130 years, so I suspect it's not going to go anywhere. Unfortunately, it's displayed behind plexiglass because you really want to turn that crank on the right side and see what happens. This is not a digital computer that does calculations with bits and bytes and logic gates. This is an entirely mechanical analog computer that performs calculations with gears and wheels and pulleys. And you may find that concept a little amusing, but the calculation that this machine performs is rather sophisticated. And the way that it does it, I think, is quite clever. We have become accustomed to the concept first suggested by Alan Turing, who is on my t-shirt here, that in terms of number crunching, all digital computers are basically equivalent. All digital computers can do the same type of calculations involving numbers, just some are faster than others. In contrast, analog computers are by their very nature rather specialized. This particular machine calculates the tides for a particular seaport. You crank the handle over at the right, and a pencil plots out the projected tides on a roll of graph paper for as long as you want to go. As I will be demonstrating, each of those 10 wheels basically generates a sine curve, and they're all added together. So what this machine is plotting is actually a Fourier summation of 10 sine curves. It is doing that calculation for continuous values of t, time. At each instance of time, it's summing 10 sine curves. Now, this tide predicting machine was the brainchild of a man who was, at the time, Great Britain's most esteemed scientist, William Thomson. By heritage, Thompson was Scottish. His ancestors had moved to Northern Ireland in the 1600s. He was actually born in Belfast. He attended Cambridge, like all very smart British boys, and then got a position at the University of Glasgow, where he taught for 53 years. What he taught would be classified today as mathematical physics. At the time, in the 19th century, it was known as natural philosophy. Now, usually when you see photos of Victorian scientists. They're old guys with white beards. And that's why I love this photograph. This is William Thomson at the age of 28. The year is 1852. And he had just done his most important work in the field of thermodynamics. I will have a little more to say about thermodynamics later in this talk. After conquering thermodynamics, around 1854, Thomson began to get deeply involved in the project to lay the first telegraph cable to connect Europe and the New World, called the Atlantic Cable. This cable involved enormous problems. If you can imagine a single cable going 2,000 feet under the Atlantic Ocean. You have to worry about the resistance of the wire, obviously. But also the effect of induction, because the cable is sitting in water, which is a conductor. So it functions as a massive capacitor. And there were many disputes about the proper proportions of copper and insulation to minimize the capacitance effect. Thomson also did some research into how the purity of copper affected resistance. He found that little impurities, and the resistance would spike up. He invented a telegraph receiver that was able to respond to extremely degraded signals. He even got involved in the mathematics of coiling the cable so that it could be uncoiled and dropped off the back of the ship without kinking. As a result, the first telegraph communication between President Buchanan and Queen Victoria occurred in 1858. That cable soon stopped working, however, and then the American Civil War started, and that caused a lot of political tension between the US and England. And so a really successful cable wasn't put down until 1866, at which time Thomson was knighted. It was also about this time that Thomson began getting interested in the tides and started contemplating this tide predicting machine. Now, a knighthood is pretty cool, but in the grand scheme of things, it's pretty common. These days, even pop singers and actors get knighted. Even Roger Moore got knighted, and he was the worst James Bond ever. Even Paul McCartney got knighted, so obviously it doesn't mean all that much. However, much later in his life, Thomson received an honor never before given to a scientist. Now, normally, this is something bestowed on generals and explorers. For Thomson, it was kind of a lifetime achievement award. He was made a baron. He was allowed to sit in the House of Lords. There was already a Lord Thomson, so he got to choose his new name, and he named himself after the River Kelvin, which winds around the University of Glasgow. Obviously, the Kelvin temperature scale is named after him. There's some other equations and scientific phenomena that are named after Kelvin. Because he got this, he became Lord Kelvin very late in his life, long after he did his most important work. I will tend to refer to him as William Thomson. It was while involved in the 1866 Atlantic Cable expedition that Thomson began getting interested in sailing and boats. He later bought a big ship himself. He became acquainted with current theories involving tides. He began searching out tidal data because he had an idea that there might be a better way to analyze and predict the tides. Now, in order to build a tide predicting machine, or to even on the computer, you need to understand what the tides are and how they work. We happen to be very near the shoreline of a large body of water. If you run outside, not now, stay here right now. If you run outside, you will notice, first of all, that there are waves that lap at the beach several times a minute. They cause people to bounce up and down in the water. These are largely the effect of wind. Quite separate from the waves is a much slower process where the water creeps up the shore and then goes back again, approximately once every 12 hours and 25 minutes. These are known as the tides. Now, although the tidal cycle is about 12 hours and 25 minutes, if you look up in the sky at every other high tide, if you look up in the sky every 24 hours and 50 minutes, you'll discover that the moon is in the same approximate progress in its apparent arc across the sky. Now, this relationship between the moon and the tides was discerned by ancient Arab, Chinese, Indian civilizations. The ancient Greeks knew about it. They also noticed that high tides were highest at full moon and new moon. These are called spring tides, referring to the water springing up higher than it is normally. The high tides and the low tides are least extreme at the time of first quarter and last quarter, and these are called the neap tides. Now, these early observers of the tides had several theories, including how maybe the moon heated up the waters of the sea, or maybe affected the atmosphere in some way. But better theories began being developed around the same time that the heliocentric view of the solar system was proposed by Copernicus. And there were several attempts at more scientific understanding. In the 1500s, William Gilbert suggested that the moon might exert a kind of magnetic influence on the seas, rather similar to our modern concept of gravity. But still, even with that, the tides present a particular problem when analyzed strictly in terms of gravitation. So let's first assume that the Earth is entirely covered by water. You know that movie where the Earth was Waterworld, right? Kevin Costner, he started developing gills so he could swim around like a fish. Anyway, so this is Waterworld. We're also going to ignore the sun for a while, and we're just going to look at the Earth, entirely covered with water. It's rotating on its axis, which is that blue thing in the middle. The moon is revolving around the Earth, as seen from the North Pole. This is not to scale, obviously. It's also moving at the rate of 1 day per second. Okay? Now, the green ball inside is the Earth. The blue is the water on the surface of the Earth. The little red dot is a particular location. It's a little red star, actually. Perhaps right here. There's a big red star here. Now, as the Earth rotates on its axis once every 24 hours, we come back to the same place. But in the interim, the moon has also moved a bit. So we see the moon at the same location in its arc across the sky about once every 24 hours, 50 minutes. That period of time is called a lunar day. And so the bulge of the high tide follows that moon. But there's also a bulge on the opposite side of the Earth. On the other side of the moon. So the high tides come at the frequency of half the lunar day, or 12 hours and 25 minutes. Now, with our knowledge with our modern day knowledge of gravity, the one high tide bulge facing the moon makes a lot of sense. The moon is pulling the water away from the Earth. The other high tide bulge on the other side of the Earth does not make any sense. Even if we completely understand gravity, it does not make sense. And we may find it very puzzling, and it's not entirely clear why it exists. Now, in the early 1600s, Johannes Kepler proposed that the moon exerted a pull on the waters of the Earth. But obviously, that only explains half the tides. And he really had to perform a lot of hand-waving to account for the high tide on the other side. Galileo, however, well, it was not Galileo's finest hour. Galileo actually ridiculed Kepler for believing that the moon exerted what Galileo called occult properties over the waters of the Earth. Instead, Galileo thought that the moon had nothing to do with the tides, that it was only coincidental. Galileo thought that the tides were caused by a combination of the Earth's rotation on its axis and its revolution around the sun. So the sunny part of the Earth is moving opposite to the Earth's orbit, while the dark half of the Earth is moving in the same direction as the Earth's orbit, thus causing the ocean's water to slosh around like in a basin. So to Galileo actually used this as a proof that the Earth was moving, as proof of Copernicus's heliocentric model of the universe. But it was certainly one of Galileo's biggest blunders. In 1687, Isaac Newton published his monumental mathematical principles of natural philosophy, commonly known by the Latin nickname, the Principia. Among many other phenomena, the Principia boldly confronts this problem of the tides, and as usual, Newton nails it. The key to understanding the other bulge is that the moon is not simply revolving around the Earth. the Earth and Moon are actually rotating around each other at a point called the barycenter, the center of gravity. This point is about 3,000 miles from the center of the Earth. It's about 1,000 miles below the Earth's surface. So that the actual center of rotation is that black ball that looks something like this. And when we see the Earth and the Moon mutually rotating around that point, the reason for the second bulge becomes a little more apparent. On the side of the Earth opposite to the Moon, the waters are being thrown away from the Earth due to the effect of centrifugal force, which we know is actually a form of inertia. If the Moon did not exist, we'd still get tides from the effect of the Sun, but the tides would be every 12 hours, half the solar day, rather than half the lunar day, and a little less than half the intensity of the Moon. So with the combined effect of the Sun and the Moon, we get a composite tide. The spring tides occur at full moon and new moon when the Sun and Moon are aligned. The neap tides are when the Moon and the Sun are at right angles relative to the Earth. The other planets in the solar system have no discernible effect on the tides, even when the other planets are in conjunction. About every decade or so, there's a book published that claims that when certain planets align in like 2 years from now, things will go crazy on the Earth. And has it happened? No, it's never happened. Now, of course, this is a simplified two-dimensional view. In 3 dimensions, it gets much messier because the Sun and the Earth or Moon are not in the same plane. The orbits are elliptical. That affects the intensity of tides, the regularity. There are other cycles involved. So tides are different at different parts of the Earth. And moreover, I started out with the assumption that water covers the entire planet. And if there's anything we can be sure of in this uncertain life, it's that the real world is not like a bad science fiction movie starring Kevin Costner. Now, what I just went through is called the equilibrium theory of the tides. There's also a dynamical theory of the tides involving looking at individual locations where you have a complex configuration of land and water. And in real life, you get about a 3-hour lag between the Moon and the tides, and you get hydrodynamic effects. These were first started to be analyzed by the Marquis de Laplace in the early years of the 19th century. Some land configurations amplify the momentum of the tides. Some land configurations dampen the tides. Tides can actually be quite erratic. Also, once the water starts moving back and forth, the same thing happens as when you pluck a string on a guitar or blow into a clarinet, you get harmonics. So not only do you get like 12-hour cycles or 12-hour 25-minute cycles, you also get cycles of 8 hours, 6 hours, 4 hours, and so forth. There's something called short period tides that are particularly exaggerated in shallow waters. Now, except for really simple cases, you can't start predicting tide patterns for a particular location in an analytical manner based on land configurations. There's just too many variables. It's too chaotic. So where do tide tables come from? Tide tables have existed for centuries. Now, traditionally, for a certain port, there'd be some guy who would put together the tide tables. He would be looking at the tide, he would be measuring the tides every day, and he would discern certain patterns kind of intuitively, working out the numbers, and he'd develop a secret technique and pass it on to his son, who would carry on the work. Beginning in the 1830s, automatic tide recorders were deployed to keep track of the continuous level of the tide recorded on paper in a big graph. And so this historical data really cried out for a different approach of analysis and prediction. And so, in 1866, William Thomson began contemplating a better approach, and he was in a unique position to do so because he was a big fan of a book written by this guy. Now, Fourier had a very dull life until the year he turned 21, and the French had a revolution. he got very much involved in the French Revolution, which was not entirely a safe occupation, because one week you could be playing a very influential role in administering the new needs of the revolution, and the next week your head could be falling into a basket. And in fact, Fourier was arrested a couple of times. In July 1794, he spent a very nervous 10 days in prison, right before the fall and execution of Robespierre. But he survived, and he survived very well. In 1798, he was recruited as one of 167 scientists to accompany 55,000 other men to go to Egypt. This was a massive expedition to investigate Egypt by the French, and it was under the command of a general who was rising in the ranks, named Napoleon Bonaparte. Fourier was later a mentor to the young man who translated the Rosetta Stone that was found during this expedition. Fourier was the person responsible for organizing and publishing the 23 volumes describing Egypt and essentially founding the field of Egyptology. In the early 1800s, back in France, Fourier began experimenting with the propagation of heat and to develop mathematical descriptions of what he learned. He analyzed the flow of heat through solid objects. For example, if you heat up a metal bar to a uniform temperature and then put a couple of ice cubes at the two ends of the bar, what happens? Well, the bar eventually cools down, but starting at the ends and working inward over time. So the flow of heat, or the flow of heat away from the bar, through a solid object depends on both time and position. And because there are two variables that change over the course of time, Fourier really pioneered the use of partial differential equations. And also the mathematical series that bears his name, the Fourier series. Now, what Fourier discovered in his research and in his math was that any complex waveform can be represented by the sum of sine curves, whose frequencies are integral multiples of a base frequency. But in many ways more useful if you know that a particular complex waveform is actually composed of smaller cyclical patterns. You can extract those and reproduce the waveform from them. Fourier described his findings in a book entitled The Analytic Theory of Heat in 1822. This is a book that British scientists of the 19th century loved and worshipped. Even though they had to read it in French, an English translation did not exist until 1878. William Thomson, he was a bright young boy. He totally devoured Fourier's book in the space of 2 weeks when he was 15 years old. He later referred to the book as a mathematical poem. This was possibly the most influential book on 19th century British physicists. Now, Fourier analysis has come to be an extremely important tool for dealing with cyclical processes. And sometimes when it's not quite expected. Fourier analysis shows up in data compression technologies such as JPEG, MPEG, and MP3, where it's used to break down the raw data and eliminate those elements to which human perception is much less sensitive. Even in the mid-1800s, Fourier analysis was recognized by scientists such as Hermann Helmholtz as having applications in acoustics. I have not been able to establish this, but I am fairly sure that the first application of Fourier analysis to real-world data was William Thomson's work with the tides. At the annual meeting of the British Association for the Advancement of Science in 1867, a committee was created, quote, for the purpose of promoting the extension, improvement, and harmonic analysis of tidal observations. The term harmonic analysis was invented by William Thomson. So the British Association for the Advancement of Science allocated £100 to the committee for expenses, and thus began the project that led to the creation of the tide predicting machine. So, what is the harmonic analysis of the tides? Let us begin with some raw data from a tide gauge. You'll probably want data points every hour or so. Here is a month's worth of data. for the Royal Harbor of Ramsgate on the South English coast, about 15 miles from Dover, for the year 1864. This is actual data that was published around that time. This is just a month. In real life, you'd probably want a year or more. This is just a month. Notice how the tides get more extreme twice during the month. That's new moon and full moon. So you then perform a Fourier analysis on it with the pre-knowledge that certain cycles are going to be there. You break down the composite curve into a series of simple sine curves. Here are the 6 strongest components of this particular tide. Each of these sine curves is defined by just 3 numbers: our frequency, an amplitude, and the phase, which is the starting point. All 6 of these have different frequencies, but they're all in the range of either 12 hours or 6 hours. Now, as you may know, the job of extracting the sine curves from the raw data is computationally intensive. Today, of course, we wouldn't dream of doing it on anything other than a computer. William Thomson was, keep in mind, a professor at the University of Glasgow. He had a different type of computational resource. He used students to do the calculations. Later on, William Thomson's older brother James developed an interesting mechanism to perform these calculations. This led to another analog computer called the harmonic analyzer, which I'm afraid I won't be able to discuss today. Now, once you've broken down that complex data into a series of sine curves, predicting future tides becomes conceptually very easy, because all you have to do is let the component sine curves continue and add them up. And then you get the predicted tide down at the bottom. Now, it is this calculation that was the job of the tide predicting machine, which in Thomson's words substituted brass for brains. I just thought that curve was not going to behave right. Anyway. Now, to perform this calculation entirely in hardware, we basically need 2 things. We need a way to generate multiple sine waves of various frequencies of amplitudes, and we need a way to add them up. It is hard for us who have grown up immersed in digital technologies to think in these terms. Our brains have become entirely warped by discrete mathematics. We cannot think in terms of analog solutions anymore. To us, everything is a number. But numbers are really artificial. Numbers are really just man-made representations of real-world dimensions. In theory, it's very easy to design a piece of hardware that generates a sine curve. When you turn a wheel with uniform angular velocity, any point on the wheel sketches out a sine curve. But this would be a little hard to actually realize in real hardware because of that blue bar that keeps changing size as it goes around. There is actually a mechanism that converts rotational movement in a wheel to linear sinusoidal motion. It's called the Scotch yoke, sometimes also known as the slotted crosshead. I've tried to research the origins of that term Scotch yoke in Google book search. I'd like to know where the term came from, not only because I'm part Scottish, but it appears first to be used as a slur in an English cartoon where it appears as a label on a pillory, one of those things where you put the guy's head and 2 hands in, in the town square, and it's labeled Scotch yoke. It's just terrible. The engineering usage actually seems to have dated from the 1880s. It's often described as having been used in old steam engines. As you can see, the wheel has a little knob or something that slides back and forth in this teeth-shaped piece, which moves up and down in the form of a sine curve. Now, the tide predicting machine needs to generate multiple sine curves of particular frequencies and amplitude. The frequency is how fast the wheel turns, and you can do that with gears. The amplitude is where you put that little knob relative to the center of the wheel. You also need to account for the phase angle, which is the starting point of the sine curve, but that's just where you set the initial position of the wheel. So let's build a tide predicting machine, at least in WPF 2D graphics. Let's fit an axle that contains a handle to right to crank, turn it around. The axle also contains a number of gears. We're working with 6 components, so we have 6 gears of different sizes because the number of teeth in the gears will determine the frequencies of the components. Next we add 6 other assemblages. You're looking at them sideways, but down at the bottom you have Scotch yokes, and those Scotch yokes are pushing the wheels up and down in a sinusoidal wave, which kind of looks like bouncing lollipops, I think. I really would like to do this in 3D someday, but there it is. Now this up and down motion is sinusoidal, so we have 6 sine curves being generated right here in real time. We need to add them up and print the result. And to do that, we can string a wire or something through them. And you anchor that wire over at the right, and you weigh it down on the left, and you put a pen or a pencil in there, and you can plot out the tides. I don't know about you, but I find this thing very elegant. One of the things that I find interesting about analog computers is that they perform comparatively complex calculations in a very natural way that makes the digital computers look rather kludgy. And you know how a computer calculates the sine of an angle, right? The static math.sine method, you know. No. Internally, it's done by the math coprocessor, but it sums up a bunch of terms to get just one sine value. And here we have a sum of several sine curves continuously plotted. In comparison, a digital calculation can only give the illusion of continuity. People did not make analog computers to do routine jobs like adding or subtracting. They perform very complex tasks. Before there were any working digital computers at all, there were analog computers that solved differential equations in the 1920s. That is the subject of my keynote tomorrow morning, if you're still interested in this stuff when I'm done. Analog computers are better suited for dealing with real-world phenomenon, and pretty much nothing describes real-world processes better than Fourier summations and differential equations, because they mimic real-world processes. Digital computers get the job done much faster, of course, but much less elegantly. On a digital computer, everything is brute force. Now, the basic design of Thompson's tide predicting machine was used in many other machines around the world for almost a century. 2 of these were from the US, and then one from Brazil, and one from Germany. I think that is the Brazil one. I think this is the German one. And as digital computers, however, became more feasible, this job was entirely shifted to software, obviously. But the basic mathematics remain the same. This is how tide tables are constructed today. So, I have discussed the who, what, where, when, and how of the tide predicting machine. I have not explored the why. And in this case, the why seems unnecessary. It's science. It justifies itself. Moreover, let us not forget that Great Britain was at this time the largest imperialist empire the world had ever known. And having a good handle on the tides is essential for commerce, industry, particularly for a country that exists on an island. And you probably won't find it surprising that one of the very first tide predicting machines was not for a port in Great Britain, but a port in India. So the tide predicting machine benefited both science and empire. And it's way cool. What more do you want from a computer? However, there was another reason that William Thomson got interested in the tides in the first place, and it involves a clash between science and science, which is difficult. Now, in one corner, we have geology, and in the opposite corner, thermodynamics. Let the battle begin. Some background. In the century between 1750 and 1850, there occurred a revolution in geology that was in many ways as profound as the earlier revolution in astronomy. We all know the astronomical revolution. It involved the familiar names of Copernicus and Galileo and Kepler and Newton, and it entirely reoriented our perspective from originally thinking of Earth as the center of the universe to thinking of the Earth as one planet orbiting a sun, much like millions of other stars. Now, what that astronomical revolution did for space, the geological revolution did for time. And like the earlier revolution, it completely redefined man's place in the cosmos by demoting our primacy. This geological revolution was led by a vanguard of natural philosophers and natural historians, many of them English and Scottish, who had stopped looking at the stars, were now examining the world below their feet. In 1750, which is the approximate beginning of this revolution, it was believed by many learned people, including scientists, that the world was only several thousand years old. Even for people who rather doubted the biblical explanation of the origin of the world and living species, there was still a strong tradition of the world being specially created and not being very old. But as geological formations were uncovered as a result of technologies such as mining, these were explored more and more, and they seemed to reveal a much older Earth. By 1795, Scottish geologist James Hutton was able to write of the age of the Earth, "We find no vestige of a beginning, no prospect of an end." Now, the geologist who did more than anyone else to wean the Victorians off biblical chronology was Charles Lyle. In the early 1830s, the 3 volumes of Principles of Geology were published. They remained popular for much of the rest of the century. Even if you read these books today, Lyle's writing has a calm, persuasive dignity that still has a really profound impact on the reader. The subtitle of Lyle's book was "Being an Attempt to Explain the Former Changes of the Earth's Surface by Reference to Causes Now in Operation." So instead of assuming that major catastrophic events had occurred in the past, like a big flood, he assumed that the past was much like the present, and that the world changed because of long-time gradual processes such as erosion and sedimentation. Hence, this geological theory was called uniformitarianism. It's often surprising to people today to learn that by 1850 or so, this work was so influential that virtually every British scientist, every well-read layperson had really abandoned a belief in the biblical chronology of the world. Even much of the Anglican clergy in Great Britain accepted the implications of geology. One scholar of the Victorian Church writes that by the 1850s, educated clergymen were saying that for many years, no man of sense had believed in a creation of the world during 6 days of 24 hours. But this discovery of what's sometimes called deep time caused some confusion. It wasn't clear how living things, in particular human beings, came about. Moreover, some people started thinking that the world might very well have existed for all time, that the world was eternal. This was considered, from a theological perspective, a very atheistic idea, because if the world had been around forever, then it wasn't actually created. And this concept was very bothersome to some people. Now, the geological revolution was not something that William Thomson was much interested in. It was pretty much over by the time he came of age. William Thomson's major claim to fame was thermodynamics. And like most physicists, he did this most important work of his career while still in his 20s, at about that age. Thermodynamics is basically the study of energy and heat. It has a very complex history in the annals of science history. It involves very many people. The history changes dramatically if you tend to look at it from a French perspective or a German perspective or a British perspective. Part of the impetus for the study of thermodynamics was in attempting to understand how a steam engine worked. It seemed to work very straightforwardly, but to actually get a grip on the science was difficult. And for a steam engine transferred heat into work, that much was obvious, but for a long time there wasn't a good understanding of what heat actually was. So Thompson was able to consolidate the work of several people, most prominently Sadi Carnot, who theorized that work was done when heat passed from a hot body to a cold one. James Joule developed an equivalence between work and heat, using weights to turn paddles in waters and measuring the increase in temperature. On one major issue, Thompson was scooped by a Prussian-born physicist named Rudolf Clausius, who published his first major article on work and heat in 1850, who later went on to invent the word entropy. But in 1851, Thompson spelled out two propositions which just a few years later became the first two laws of thermodynamics that we still know today. Around this time as well, Thompson began using a particular word. That this word existed, but it had no previous technical meaning. That word was energy. Now, energy takes several different forms. We can often transform one kind of energy into another. For example, a common flashlight battery, chemical energy, is transformed into electrical energy. Heat, which we know now to be the microscopic movement of molecules, is also a form of energy. And it's usually very easy to get heat from other forms, where we can rub our hands together to turn kinetic energy into heat. When we're using electricity, heat is generated, whether we want it or we don't. In fact, whenever you're transforming energy from one kind to another, heat is a very common byproduct, and it can't be avoided. So, the first law of thermodynamics says energy is conserved. You can't create energy, you can't destroy energy. The second law of thermodynamics says that heat is special. Heat is the unrecyclable garbage dump of energy. You get heat from every other energy conversion, but going in the opposite direction is much harder, because heat by itself cannot be converted into other types of energy. Only when you have a differential in temperature can that heat be transformed into other forms of energy. And then, never with 100% efficiency. Once that temperature differential is lost, once the hotter thing has become the same temperature as its surroundings, you can't convert the remaining heat into energy without the expenditure of some other kind of energy. Often people think, wouldn't it be great to use all the heat stored up in the ocean as an energy source? Well, you can't do it unless you have an engine that connects two parts of the ocean with very different temperatures. There are very many perpetual motion machines that attempt to extract energy from heat without that temperature differential. They just don't work. Nature has a bias against heat, and this bias is what gives direction to the universe. It defines the arrow of time. While energy remains conserved, the entropy of a closed system, basically the measure of unavailable energy in the form of heat, always increases. Now, William Thomson was one of the first people to grasp that these thermodynamic laws had a really cosmic significance. See, thermodynamics implies that the universe doesn't exist in a stasis. In the distant past, there was much less entropy than there is now, and in the distant future, there will be much more entropy. And eventually, the universe will run down. All the energy of the universe will become heat. The whole universe will be equal in temperature, and that's that. That's the famous heat death. So Thompson realized that people who went around talking about the eternity of the universe were simply wrong. If the universe were infinitely old, it would have run down by now. the universe had to have come into existence with less entropy than it has now. And according to Thompson, that means that the whole geological theory of uniformitarianism is also flawed because the very nature of the universe and the Earth changes as entropy increases. So in 1852, in a little article entitled "On a Universal Tendency in Nature to the Dissipation of Mechanical Energy," Thompson wrote, "Within a finite period of time past, the Earth must have been, and within a finite period of time to come, the Earth must again be, unfit for the habitation of man, as at presently constituted, unless operations have been or are to be performed which are impossible under the laws to which the known operations going on at present in the material world are subject." Now that whole last half of the quotation refers to something we commonly call a miracle. But without miracles, as far as living things are concerned, the Earth has a beginning and an end. And the length of that period of time in between is governed by thermodynamic forces. So 7 years after this little article, on November 24th, 1859, a book was published that really brought this whole issue to a head. Charles Darwin had read Charles Lyell's Principles of Geology while traveling around the world, serving as a naturalist for the HMS Beagle. Lyle essentially gave Darwin the permission to think in terms of long periods of time. And in the pages of The Origin of Species, Darwin wrote, "He who has read Sir Charles Lyell's grand work on the Principles of Geology, which the future historian will recognize as having produced a revolution in natural science, yet does not admit how incomprehensibly vast have been the past period of time, may at once close this volume." These incomprehensibly vast periods of time were necessary for the process of natural selection to occur. For certain offspring to have slight differences that favor their survival and procreation over their brethren, and for these offspring to pass on these characteristics to their descendants. Now, at the time, what bothered a lot of people about the theory was the seeming randomness of it all. Some people, and still to this day, can't tolerate the idea of a process that is obviously of immense importance to us, for we are part of it, but which also seems inherently directionless and unguided. And one of the people who found natural selection to be somewhat distasteful to his sensibility was William Thomson. But for a scientist in one discipline to criticize another scientist in another discipline was very tricky. There was a certain propriety in staying within one's own field of scientific knowledge. A physicist couldn't just come out and criticize geologists or zoologists unless those geologists or zoologists encroached into the area of physics. So if the evolutionists were directly contradicting some basic principle in physics, then that's fair game. And so in the early 1860s, William Thomson began wondering, could the age of the Earth be estimated through physics? And Thomson tried to determine how long the sun could burn. And if you assume it's a burning liquid or a burning gas, such as might occur on Earth, it doesn't burn for very long. The sun burns out so quickly, like a few million years, that it's obvious there's something obviously wrong with your assumptions. And so Thomson had to come up with theories about how the sun was constantly replenished with meteors falling into it. It's a little painful to read some of those papers. A much more fruitful inquiry involved the age of the Earth. Now, if you do the calculations, you will find that the sun alone is not sufficient to account for the warmth of the Earth. There's got to be something else besides the sun that keeps the Earth warm. It was also known from experiences in mining that if you dig further down, the more you get into the Earth, the warmer it is. And from that, we can perhaps deduce that the Earth is cooling down from some very hot prehistoric state. Perhaps it started out as a globe of molten rock. And see, Thompson knew how to do these calculations. That's what Fourier's book was all about. It was about objects that cool down or get heated up, and how this changes over time. So he could work out the formulas backwards and figure out how long ago the Earth was molten and hence unsuitable for life. And in 1862, Thompson published his first estimate that the Earth had been suitable for habitation between 20 million and 400 million years. This was much less than the evolutionists wanted. Over the subsequent decades, he continued to refine these calculations. At one point, he got down to 10 million years as the age of the Earth. And he continually criticized the geologists and evolutionists for persisting to believe that the Earth was older than his calculations showed. And it really did sting. This is, if you read any book on famous controversies of the scientific controversy of the 19th century, this is one of the biggies. Thompson was the major scientist of the British Empire. And physics was a hard science, and geology was a soft science, at least somewhat softer. And Thompson was basically accusing the geologists of ignoring fundamental laws of the universe. But around 1866, Thompson suggested a possible reconciliation between the facts of thermodynamics, which implied a relatively young Earth, and the apparent observations of geologists, which suggested a very old Earth. As the moon revolves around the Earth, and as the Earth rotates under the moon, and as the Earth revolves around the sun, we have seen that tides result. Water is constantly moving back and forth across the solid Earth. There's friction involved. There's heat generated. There's a loss of kinetic energy, resulting in the rotation of the Earth slowing down. This is a phenomenon known as tidal retardation. Now this could reconcile the physicists and geologists in this way. Suppose the Earth was only as old as Thomson's heat analysis revealed. But in the past, the Earth was spinning faster on its axis. Hence, there was much more turbulent activity occurring, hence causing a lot of geological damage that is today being interpreted incorrectly by the geologists as indicating a long Earth. But Thompson realized if the Earth is not as old as the geologists believe, it's probably not old enough for evolution to occur. Can tidal retardation be quantified? Now, in order to do that, we would need numbers describing how tides actually work. And this, besides the obvious commercial potential of tide predicting machine, was one of the rationales for the harmonic analysis of the tides. So, aside from its scientific value, and in commerce and empire, the tide predicting machine can also be viewed as a primitive armament in the 19th century Darwin Wars, which I think makes this whole thing rather more ominous and also more interesting. Now, it's often said that history is written by the victors. Scientific history is no different. History has not been kind to William Thomson. Much of the problem involves that age of the Earth controversy. He was very obstinate about it. He persisted in it for a very long time, decades. He would not admit that other factors could be involved that he might be missing. His work and his advocacy was obviously precipitated by his distaste for Darwin's theory of natural selection. Of course, it wasn't personal. In fact, around 1877, Thompson got an assistant, a young scientist who was very interested in the tides and the formation of the moon and the application of mathematics to geology. His name was George Darwin. He was Charles and Emma Darwin's fifth child. He was 14 years old when The Origin of Species was published. It was George Darwin who later published a major book about the tides. This book is still eminently readable. It was George Darwin who calculated the first estimates of tidal retardation and found they did not have much of as much of an impact as William Thomson had believed. He was perhaps more than anyone else founded the science now known as geophysics, which is using principles of physics to better understand geology. Now, Thompson's calculations of the age of the Earth were correct with what he knew and what he assumed, that the Earth was a cooling, molten globe. They were wrong because he was missing something. And a significant clue to the mystery of the Earth's age came about with the discovery of radium in 1898 by Madame Curie. As radium decays, it emits heat, and there is sufficient radium and other radioactive materials buried in the Earth to add significantly to its warmth. If it weren't for the radioactive material in the Earth, we would all be very cold. Ernest Rutherford gave a lecture on radium in 1904 with William Thomson, the old William Thomson actually in the audience, and suggested that radium was the solution to the age of the Earth controversy. The Earth really was as old as the geologists believed. And just a few years later, radioactive materials began being explored as tools in dating the Earth. And it is now estimated that the Earth is about 4.5 billion years old. Thompson was alive in 1905, which was the miracle year of Albert Einstein. I cannot find any evidence that William Thomson knew of the young German's amazing publications of that year. One of those papers proposed an equivalence between mass and energy, eventually solving another problem that Thompson had wrestled with concerning the age of the sun. E equals mc squared really changed the rules of how the universe works. And so life goes on, and we keep getting smarter, or at least we think we do. Thank you. We seem to have like 5 minutes if there's any questions. Or should I hand out the pop quiz? Oh, yeah. Was a weird talk like this worthwhile? Yeah. Okay, that's.
All those animations were rendered with WPF?
Yeah, this is a big WPF program. Tomorrow, for the keynote, I have a big Windows 8 program that I wrote in C++ and used Direct3D. So there is some 3D in tomorrow's keynote, but no PowerPoint. I'm sorry.